So here's the official statement of Barkhausen's, that the magnitude when it equals 1, so the magnitude of your gain is 1. In other words, the log, so your gain is 1 and the log of 1 equals 0. So your 0 dB at this point right here, then you will get positive feedback if your gain is greater than 1. Okay, so let's look at just some terms for feedback. And today we won't really do any feedback, but I'll talk about how we're going to approach feedback, and then I'm going to just introduce you to the terms shunt and series when looking at an amplifier. Okay, so here's a typical configuration that you've seen in previous classes. You have your high gain amplifier, and then you have your output, and then it goes back to this through this resistive network here. This is your F, and feeds it back to the input. Okay, so you've done that kind of abstractly with the symbol for ideal op amps, the triangle. Now you know what is inside that triangle, and a perfectly good op amp, though it doesn't have maybe the gain that you'd like in a real ideal op amp, is a diff pair. So if you wanted to implement this circuit using your diff pair op amp right here, you'd say, okay, so I have V in going into the plus terminal. All right, let's call this the plus terminal. You have V in into the plus terminal. If this is the plus input, then this is going to be the plus output. The way you figure that out is if you move this up, does this terminal go up or down? If you move this up and this terminal goes up, that means this is the plus input and plus output. They go in the same direction. So this makes this the minus input. Alright, so let's see what we've got here. We've got input going into the plus terminal. Okay, input into the plus terminal. Then we have V out. There's V out. V out goes into a voltage divider. So here's your voltage divider, R1 into R2 down to ground. All right, so we have our voltage divider, and then this says from the middle between the two resistors, there's a wire that goes back to the negative input. So here's the resistors. From the place between the two resistors, there's a wire that goes back to the negative input. And now this is your, you set this up as an op amp, as the same configuration as this op amp over there. Okay, and I'm going, if you have questions about this derivation of this equation down here, or anything like that, please come see me and we'll go over it. Right now we are going to just go through some definitions and then do series shunt, and then we'll start with actual feedback calculations on Monday. Okay, definitions. Okay, T is the loop gain, AVF. So talking about that in when we did the first slides of feedback. AV is this amplifier right here, the gain of this amplifier. F is the gain of the feedback amplifier. Multiply the two, that tells you if you put a signal in here and watched it come out here, what the gain would be. So AV times F, you've got those in series. Okay, open loop gain is just the gain of your feed-forward amplifier. So just the gain of that. That's your small AV. That's your lowercase AV. F is the gain of your feedback network. AV with a capital A, that's the gain of your entire amplifier with feedback. Okay, and for gain of the entire amplifier with feedback, if you go through all the math and your AV, in other words your forward gain, this amplifier right there, that has big gain, then you get a gain of approximately 1 over F. Okay, negative feedback, since it does lower your gain, pretty much some of these are just not a reward, but the result of lowering your gain. They're going to be less sensitive to temperature changes, device aging, various noise. since you're killing the gain a little bit. Along with that, in other words, we also had the flat band, so you had the wide banding. You have a wider range of just a flat gain to a higher frequency. Something else you get when you start using feedback, your R in and your R out will also change by a factor of 1 plus T in the direction you want them to go in. And what I mean by that is, let's say you have a current input amplifier. Well, let's go with voltage input. If you have a voltage input amplifier, you like to have your Rn equal infinity. Okay, so if you use feedback, what happens is, you like a big Rn, that means Rn is going to be multiplied by a factor of 1 plus T. That 1 plus T shows up again. If you have a current input, you like Rn to be very small. If you want all of the current to go into your circuit. So you have a low Rn if you have a current input circuit. And so when you use feedback, what happens is, just naturally, you get a new Rn of Rn over 1 plus T. Same thing with R out. If you have a voltage output circuit, you like a low R out. What happens when you put feedback onto your circuit, you get an R out over 1 plus T. Again, if you have a current output, you like a high R out. And when you have feedback on a current output circuit, what happens is R out gets multiplied by 1 plus T. Okay, and here's an example. Let's say you have an amplifier, and this is its transfer function, and you have a slope of A1 here. Let's say it's cascoded, so when Vn gets high, since you have stacked transistors, one of them goes into linear. The other one can still be in forward active, but one of them goes into linear, and that kills your slope a little bit, and then you get to the range where you have no amplification. Okay, so let's say when they're both in forward active, you get this steep A1 gain. When one of them goes into linear, you have A2, and down here I just wrote it the same way. You know, when you're going down too low, one of those cascoded transistors goes into linear, the other one's still in forward active, and then you get to the place where you get no gain. If you do use feedback with that, everything gets divided by that factor of 1 plus T. So originally you had A1 here, now you're going to have A1 over 1 plus T. Here you originally had A2, now it's A2 over 1 plus T. Okay, and again, gains divided by 1 plus T. So we're going to go through 3 passes to try to figure out how an amplifier is affected by feedback and loading. In the first pass, we are just going to look at just the feedback effect, and that's that 1 plus T. I'll show you that it is in fact the R in, R out gets either multiplied or divided by 1 plus T, and the gain gets divided by 1 plus T. Okay, in the second pass, what we're going to do is we're going to kind of forget about that 1 plus T, and we're just going to look at what feedback does to your amplifier. And in the third pass, we'll put them both together. Okay, one of the important things about going through that third step is one more name you have to remember, series shunt. And to do that analysis, you need to be able to figure out if the input is series or shunt, and the output is series or shunt. So let's just practice that, and then we'll call it a day. Here's an amplifier. And I can't, unfortunately, on my mom's computer here, I can't draw, so I'm going to point. First thing you need to do when you're trying to figure out if a circuit output and input are series or shunt is you go in, you need to identify that feed-forward amplifier, that small AV, and your feedback network, your F. Okay, the way you do that is, first of all, go in there, find the input. Okay, here's the input. Goes through RB. We'll forget about that right now. That's the source. That's the input coming into the input of your amplifier. Okay, then you find your input. What you look for is a vanilla amplifier, and what I mean by that, and vanilla is my word. You won't find that in a textbook anyplace. But a vanilla amplifier, you've seen 3 vanilla amplifiers: common emitter, common base, and common collector, or emitter follower. Okay, so what you do is you go to the input and you say, okay, I'm going to look for a vanilla amplifier, and this first stage right here, first you have to identify it, and I see a common emitter with emitter degeneration, but emitter degeneration is not the vanilla version of that amplifier. Common emitter is the vanilla version. So what I do is I draw a circle around just the common emitter part, not the degeneration, just the common emitter part. Okay, so that is going to be part of our feed forward, our small AV amplifier. Okay, now we come out of the output there. We look at this next amplifier. Okay, we have to do the vanilla thing again. And I see another common emitter. Alright, then we go over here and we look at this next stage. The output of this common emitter goes over here, goes into the base of this. First you have to identify what kind of amplifier that is. I see an emitter follower. And the emitter follower here, this resistor is absolutely necessary. It's not a follower unless it has either a transistor down here or a resistor. So this whole thing is your emitter follower. So let's see what we've gotten. We've got rid of this, this, and this. What's left are those 2 resistors. So this, and this, I think, oops, this, and this, those are your small AV feed forward amplifier. This blue circle right here is your feedback network. Okay, now for the naming, series or shunt. Okay, let's go from the input here. You see the input to your amplifier is right here, but the output of your feedback network is to this other terminal right here, to the emitter. So the input goes to the base, the feedback goes to the emitter. If you draw a path from the input to ground, you go through the base of the transistor, down out through the emitter, oops, and then you hit the feedback, go through a resistor and hit ground. So if you go from the input to ground, you have to go, it's kind of a series connection. It's R pi, and then you hit the feedback, and then you hit another resistor, and then you hit ground. So this is a series input. Okay, we'll see what a shunt looks like in a minute. Alright, and the output, let's see what happens here. There's the output of your amplifier. Your output is also your input to your feedback network. So both of them, if you are looking at the voltage for the input to your feedback network and feedback to your output of your amplifier, they both go from the same point to ground. Okay, so those are shunt. Those are across these 2 nodes. So V out to ground and the voltage into your feedback network to ground, those are across the same nodes, and that's a shunt. So this is considered a series and a shunt, series shunt circuit. Okay, and just if you put a circle around all the feed forward, the small AV circuitry, there's your small AV. All right, and let's do another one. Oops. If you look at this one, first you have to knock out your vanilla amplifiers. So right there I see a common emitter, and RC is a necessary part of the common emitter. So I see that as my AV. That's my feed forward amplifier. Okay, that means that RF and possibly RB, we'll talk about that on Monday, that's our feedback network. So let's look at the output first. Again, you have the voltage to your feedback network is equal to the voltage of the output of your amplifier. So they're both going across the same points. This node to ground, this node to ground. So that is shunt. V out is shunt. Right here, to get to your feedback point, you don't have to go through your transistor. So that's not a series. When that feedback comes back and actually hits your input node, that is always going to be shunt. So the output of your feedback network and the input to your amplifier, those are the same nodes, and they're going from that point to ground. They're going from the same point to ground, so those are in shunt. So this right here is a shunt. Output shunt, output same, V out to ground is the same as the input to the feedback network, and V in to ground is the same as the output of the feedback network. Okay, give that one a try. And here, let's see, find your vanilla amplifiers. You've got common emitter, and then you've got another common emitter. Notice the V out is at the collector, so this is a common emitter. So all these resistors down here, that's your feedback network. Okay, V out's up here. For V out to get to the input of your feedback network, it has to go through the transistor, so that now your output is series. Okay, and on the input, the feedback goes to the, if you're looking at this and this as your amplifier, the feedback goes to the same node as your input comes into, so that's a shunt. So this is a shunt over here and a series over here. Okay, and the final one for practice, and we'll see why these matter, is right here. Let's see, is V out, let's get rid of our vanilla stuff. There's a vanilla, there's a vanilla, and this is still a common emitter, so this is a vanilla here. This is degeneration for this amplifier. So the vanilla amplifier is just this up here. So all of this back here becomes your feedback network. V out and the input to the feedback network are different nodes, so that has to be series. Your feedback, so your input and where that, and so here's your feedback network. The output of the feedback network is not coming to the same node as your input, so this is series again. So it's a series input, series output. This is a series amplifier. Okay, so that's all the terms we'll go through right now, and on Monday we'll start with the analysis of feedback circuits.